Welcome back, everyone. We are in the fourth lecture of Introduction to Glass Science. We are currently in Chapter 2 of Fundamentals of Inorganic Glasses. Last time we discussed what it means to be a glass. We covered the volume temperature diagrams and discussed some of the unique properties of glass as being a non-equilibrium state. So what we're going to do today is have a quick review of the lecture from last time, and then we're going to get into some more details on the fundamentals of the glassy state, particularly in terms of its non-crystalline structure. So just a quick recap from last time. We covered the definition of glass. Glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale, but continuously relaxes toward the liquid state. And we explained this definition of glass in terms of the volume temperature diagram on the right. The fact that glass is non-equilibrium means that it is a thermodynamically unstable state. That means that it is continuously relaxing towards its metastable supercooled liquid state. And it also means that we need this additional order parameter to describe the thermal history of the glass, which is this fictive temperature here, TF1 and TF2. Now, I'm not going to repeat everything from last time, so if you have any questions about either this definition of glass or about this volume temperature diagram on the right, I will refer you back to the previous lecture, lecture number 3, What is Glass? Or you are welcome to reach out to me with questions anytime. So moving forward from a chemical point of view, the interesting thing about glass is that any liquid can, in principle, be quenched into the glassy state if you can cool it fast enough to avoid crystallization. So if we go back to this volume temperature diagram, we noted last time that crystallization takes time, right? It takes time for the atoms to rearrange themselves in the disordered liquid state to form the ordered crystalline configuration. And if you were to cool the liquid fast enough so that you don't give the atoms enough time to rearrange themselves into that ordered crystalline configuration, then that liquid can be quenched into the supercooled liquid state. And that supercooled liquid state, upon continued cooling, can be quenched into the glassy state. And the glassy state has a frozen-in liquid-like structure that comes from this quenching process, from quenching the liquid in supercooled liquid. And so any liquid, then, if you cool any liquid fast enough to avoid crystallization, it can, in principle, be quenched into the glassy state. And what this means is that from a chemical point of view, there are an infinite number of possible glasses available. Glass isn't like a crystal, where a crystal needs to satisfy certain requirements with respect to the stoichiometry of the crystal to define the unit cell that gets repeated infinitely in each direction. As a disordered non-crystalline material, glasses don't have to satisfy those same rules of stoichiometry because they don't have a unit cell. And what this means is that if we look at this periodic table, there's just about any element on that periodic table that could conceivably be incorporated into the structure of a glass. The only exceptions would be the noble gases, most likely, or it would be very difficult to incorporate them into a glassy structure. But nearly this entire periodic table is available in terms of elements that could potentially be included into the glassy state. And another byproduct of the non-crystalline structure of the glass is that the chemistry is continuously adjustable. That means you don't have to satisfy certain proportions of certain elements to each other because you can continuously adjust that chemistry of the liquid state and then take that liquid state and then quench it into the glass. Now, conventionally, there are different families of glasses, as we covered in the second lecture of this course. This was back in chapter 1. Most of the glasses that we normally think of as being glass are oxide glasses. So these are glasses that are based on having oxygen as the anion. Among those, the vast majority of those are silicate glasses. Of course, there are many other types of oxide glasses too, as we mentioned before, like borate glasses, phosphate glasses, germanate, vanadate glasses. We also have chalcogenide glasses. So if you move below oxygen in the periodic table, the next elements are sulfur, selenium, and tellurium. And if your glass is based on any of those elements, sulfur, selenium, or tellurium, you can have chalcogenide glasses. And these are known for their semiconducting properties. They are used for memory storage, for infrared transmission and switching applications because of their unique optical and electronic properties. One of the newer families of glasses that we covered are metallic glasses. In this case, the bonding within the glass is metallic. It is based on a sharing of the electron cloud between atoms. These bondings are highly non-directional. What makes it a glass? It's a glass because the liquid is stable enough against crystallization in this case that the metallic alloy can be quenched fast enough to suppress crystallization. And if that happens, then the structure of the metallic glass corresponds to the structure of the alloy liquid from which it came. So these are just three examples of different families of glasses that can be made. Within these families, there's any number of possible compositions. And one of the purposes of this course is going to be how do we kind of go about the design of glass chemistries um, from the point of view of building upon the fundamentals of the relationships between the glass chemistry to its structure and then finally to its properties here as shown in the lower right. So we're going to cover all of this in the course. We're going to cover different types of glass chemistries. We're going to study what their structures look like, and we're going to study what the impact of the structures are on the properties of the glass. And this is really a distillation of a large part of what it means to be a materials scientist or engineer, whether it's glass or some other class of material. In any case, what we want to do is understand the relationships between the chemistry of that material with its structure and microstructure, and then connect it back to its properties so we can both build that fundamental understanding, but also apply that fundamental understanding towards the design of new materials that will hopefully help enable new applications. And what makes glass so exciting is both from a physics point of view, the fact that, as shown here in the previous slide, even though glass is an old material, it is actually at the cutting edge of materials physics because of it being out of equilibrium from a thermodynamic point of view. This means that you can't just apply standard equilibrium thermodynamics and expect that it will work. You also can't apply standard crystal chemistry because this is a non-crystalline material. And you need additional parameters, you need additional understanding of how to quantify the disordered nature of the glassy state. And so this is really at the cutting edge of materials physics at the same time as being on the cutting edge of materials chemistry, since we can have any number of different types of chemistries that could potentially make a glass. And we want to go about the design of new glasses in an intelligent fashion, building upon our fundamental knowledge of these chemistry, structure, property relationships. So that's kind of, in a nutshell, what we're going to try to do with this course. Now, one of the ways that we can characterize the order or disorder of a material based on its atomic structure is using a function called the pair distribution function. So the atomic structure of glass, what we're going to see is that it exhibits short-range order but long-range disorder. And one of the ways to quantify that short-range order and long-range disorder is using the pair distribution function, which is commonly represented by this function g of r, where r is kind of the radius from some central atom. And the way that the pair distribution function works is that if we have some material with some structure as shown here, where each one of these circles is an atom, and the dark smaller circles in the middle would represent the centers of each atom. To calculate the pair distribution function, we select one of these atoms as being the central atom. So in this case, the dark atom here in the center is represented as the central atom. This, if you go vertically up from here, this vertical dashed line corresponds to 0 on the r-axis. So this would be a radius of 0 corresponds to the exact center of this particular atom in the middle. And then as we increase r, so this is moving to the right on this plot, increasing r means that we are expanding out radially from the central atom. So r equals 0 is at the exact center of this atom, and as you expand out radially, you're creating these shells that are moving, these concentric shells that are expanding out, where the center is always at the central atom here, but the radius of these shells is becoming larger and larger. So these dashed shells, you can see the circle shown here, the larger circle as it's expanding shown here, those correspond to larger and larger values of r, and where r is the radius of those particular shells. Now, what the pair distribution function does, this g of r function, which is plotted on the y-axis, is that it plots the number density of atoms found at r divided by the average number density in the limit of long distance. So if we start here at r equals 0, the pair distribution function is 0 because the probability of finding some other atom at the exact same location as your central atom is 0, right? We know that Pauli's exclusion principle from quantum mechanics forbids two atoms from being at exactly the same position. And as a result, this pair distribution function is going to be 0 because there's a 0 probability of finding another atom exactly overlapping with your central atom. Now, as we increase r, we are expanding the shell out a little at a time, and you'll see that the pair distribution function remains at 0 over some distance here. And this remains at 0 because of the repulsive nature of atoms. If they are too close to each other and their electron shells are overlapping with each other, again, because of Pauli's exclusion principle, that is going to be highly unfavorable from an energetic perspective. And therefore, the probability of finding another atom that is strongly overlapping with the central atom is going to be pretty close to 0. So this pair distribution function remains at 0 until we get to the first nearest neighbor. And when we have that first nearest neighbor, that's where we see the first peak. That first nearest neighbor peak is corresponding to this inner circle shown here. So I'm highlighting this with my laser pointer, and you can see that all of these first nearest neighbors, that means the atoms that are closest to the central atom, they're all located at roughly the same distance from that central atom. And this is what we mean by short-range order. The short-range order is telling us that there is a preferred bond distance between any given atom and its first nearest neighbor. There's a preferred bond distance. There's probably also a preferred coordination number, which would be the number of atoms that you have in this first nearest neighbor shell. There might also be preferred bond angles there. But this pair distribution function is capturing then the preference for the distance, the bonding distance between the central atom and the first nearest neighbor. So this first peak here, the first peak that you see in the pair distribution function, that peak occurs at the most favorable bond distance between the central atom and its first nearest neighbor. Now, the fact that this peak is going well above 1 means that the number density at that first nearest neighbor distance is much greater than the average number density in the limit of a large distance. So what this means is that you're much more probable to find atoms here in this first coordination shell compared to just some random distribution of atoms. And if you look at the structure, indeed, that's what you see, that if you kind of move out radially from the central atom, that the first nearest neighbors here can be found at a fairly well-defined distance out from that central atom. Now, if you keep moving out from this first nearest neighbor shell, you'll see that this pair distribution function is dropping below 1 for some distance, and that's because you are less likely to find an atom here in this kind of more of a void space between the first nearest neighbor and the second nearest neighbor. And that's because the first nearest neighbors have fairly well-defined positions. And then if you try to insert other atoms too close to them, those other atoms are going to be overlapping with the first nearest neighbors, which is energetically unfavorable. And as a result, then this first peak is followed by a trough. And then, so this is lower than 1, and it doesn't rise above 1 again until you get to the second nearest neighbor. So the second coordination shell is given by the outer circle shown here. Again, because this is above 1, this means that you're more likely to find atoms in this second nearest neighbor regime compared to just a random distribution of atoms in the limit of large distance. But what you'll notice about the second coordination shell is, first of all, it's broader compared to the first coordination shell. The fact that the first coordination shell is so narrow means that the first nearest neighbor distance is actually quite well defined. However, if you go out to the second nearest neighbor, there's a bit more randomness that gets introduced into the structure. And even though the second coordination shell is still greater than 1 here, the fact that this is broader means that the atomic positions for the second nearest neighbor are spread out a bit more. They're less well defined compared to the first nearest neighbor shell. That also gets reflected in the fact that the peak position here is quite a bit lower compared to the peak position for the first coordination shell. So again, this is indicating that we still have some order at the second nearest neighbor level, but there's less order compared to the first nearest neighbor. Now, if you move on from the second nearest neighbor shell, there'll be another trough where you're less likely to find atoms there. And if you continue on, there might be a small peak here for a third coordination shell, or it might just go to continuum where it asymptotically approaches 1. And what we get here when this is approaching 1 or exhibiting some sort of noise about 1 is at that point, a pair distribution function of 1 means that the number density at that distance is equal to or approximately equal to the average number density. And the fact that this approaches 1 without any further peaks means that we don't have any strong correlations then between the position of the central atom and the position of atoms at these long distances. So if we put all of this information together, what this is telling us about the structure of a glass is that the atomic positions of the first nearest neighbor are quite well defined. In other words, the glass has short-range order that's defining the positions of the nearest neighbors to a given atom. However, when you move from the first nearest neighbor to the second nearest neighbor, there is some degree of intermediate range order because there is some preference for certain positions of the second nearest neighbors, but those preferences are less well defined compared to the positions of the first coordination shell. If you get beyond the second nearest neighbor and go to further distances, you've got either completely disordered structure at that point or much less well ordered compared to the first and the nearest neighbors. So from the perspective of the central atom, this shell here corresponding to the first nearest neighbors, that's well defined. The second nearest neighbor shell here, this outer ring, is moderately well defined, but then moving on from there, there's a lack of correlation between the position of the central atom and any atoms beyond that. So this is what we mean when we say that glass exhibits short-range order, and it exhibits some degree of intermediate range order, but it is completely lacking in long-range order. And it's these same type of features that you would find in the liquid state as well, because the glass is inheriting its structure from the structure of its parent supercooled liquid. Now, what I just described was G of R, which is the pair distribution function. You will often see in the literature another function being described, which is called the radial distribution function, or the RDF. Now, some people will use these terms interchangeably. Some people will use the term radial distribution function to mean the same thing as the pair distribution function G of R. And in that case, it would be plotted exactly as shown here with this pair distribution function. Strictly speaking, though, the definition of the radial distribution function is actually the pair distribution function here, G of R, multiplied by 4 pi r squared times rho 0, which is the average number density here, which would be found in the denominator. And what this means is that this 4 pi r squared, this is the surface area of this shell that is expanding out. So if you start at the central atom here, that has r equals 0, and then expand out from there, these spheres, these shells, are expanding out radially, and the surface area of them, of each one of those shells, is given as 4 pi r squared. And if you take that 4 pi r squared multiplied by the number density and then multiplied by the pair distribution function, the area of that would give you the number of atomic neighbors that reside between the two limits of the integral. So in other words, the radial distribution function, or the RDF, if we plot that, it's going to have a lot of the same features from the pair distribution function, including being 0 at low values of r, having a first peak, followed by a trough, followed by a second less well-defined peak, followed by another trough, followed by complete randomization of the glass structure. But this gets multiplied by a parabola. It gets multiplied by 4 pi r squared rho 0. And so multiplying that by this parabola, where this parabola is shown by the dashed line, instead of having the peaks and the valleys oscillating around a constant 1, what they end up doing is oscillating around that parabola. And then if you integrate this radial distribution function, integrating it between two different r values, so between, say, r1 and r2, the area of that integral is going to give you the number of neighbors residing between r1 and r2. So integrating the radial distribution function is like counting the number of neighbors. So for example, for this shell here, let's suppose that we got this first nearest neighbor shell. If we've got R1 and R2 to define some range of R values there, and if you integrate all of that, and that integral then would give you the number of neighbors that's expected, which for this particular diagram would be 5 atoms in that shell. If you're to do the same thing for the second nearest neighbor, integrating the RDF for that second nearest neighbor, that would give you the number of atoms found in the second nearest neighbor shell, and so on. Now, when the radial distribution function is approaching the parabola, that's the same thing as the pair distribution function approaching 1 and reaching continuum. At that point, you have just a complete randomization of the structure because there's a lack of correlation between the central atom position and the atomic positions at those large distances. So in that case, the G of R just reduces to 1, and then the number of atoms is basically given by or governed by the number density here, rho 0, and then the limits of your integral between R1 and R2. So these are both useful functions that give you the same information as each other, which is how likely you are to find atoms in certain locations compared to others. But you can use these functions a little bit differently depending upon what's convenient for the particular problem. And like I mentioned, sometimes people will use these terms interchangeably, but strictly speaking, the radial distribution function is oscillating around this parabola, whereas the paradistribution function is oscillating around g of r is equal to 1. Now, much less often, occasionally, you will see some other similar functions defined that have exactly the same information, but the definitions are slightly different. These are much less commonly used than either the pair distribution function or the radial distribution function. So I am just discussing them right now for your information, but I'm doubtful that you will actually find these used very often in the literature. One of them that can be defined is the total correlation function. The total correlation function oscillates around a line of 4 pi r rho 0 rather than the parabola of 4 pi r squared times r0. So this is the same thing as the radial distribution function, but just divided by r. So it's just 4 pi r. And in this case, this line here is 4 pi r rho 0, and then the total correlation function is oscillating around that line. This is not used as much as the radial distribution function because the radial distribution function can be integrated to get the total number of neighbors, and that's not possible with this total correlation function. Sometimes the total correlation function is used just because it's more convenient to see some of the oscillations around a line compared to seeing the oscillations around a parabola. Another function that can be defined is the differential correlation function. The differential correlation function is taking the pair correlation function and then subtracting out that linear part, so subtracting out the 4 pi r rho 0, and in that case, the remaining function, after you subtract out this line, is really oscillating around 0. So in this case, the 0 means a lack of any type of correlation between the atomic position at r equals 0 and the atomic position at some other distance r. However, if you can have a positive correlation if it is above 0. A positive correlation means that you're more likely than random to find an atom in that position. If the differential correlation function is negative, that means that you're less likely than random to find an atom at that position. So that's how it's used, meaning that the positive values of the differential correlation function indicate that you are more likely than just a random distribution to find atoms at those locations. And if the differential correlation function is negative, then you're less likely. Now, what do some of these pair distribution functions look like for various phases of matter? Let's start with the crystal here. The crystal in the lower left corner. The structure of the crystal consists of unit cells. The unit cell tells you the kind of basic structural unit that gets repeated in all 3 directions. And what this means is that for a crystalline material, the atomic positions in principle are perfectly well known and perfectly well defined. And so if we plot the pair distribution function for a crystal, what you'll see is that there are very sharp peaks. These sharp peaks occur at well-defined positions, and the intensities of those peaks would tell you how many atoms are being found at those various positions. So this gives you very sharp, well-defined peaks, not just at short distances and intermediate distances, but at long distances as well. If you have a perfect single crystal, then all the positions for all the atoms are always perfectly defined and perfectly well known, which would give you always perfectly sharp peaks here in the pair distribution function. If you have a polycrystalline material, then you start to lose correlations anytime you cross a grain boundary and go from one crystal to the neighboring crystal, especially if there's a change in orientation. Now, if we take the opposite extreme, the most disordered phase of matter would be a gas. And if you have a monatomic gas, this would be like a noble gas like argon or neon. Here, the pair distribution function is 0 at short distances because of Pauli's exclusion principle. This means that you cannot have the atoms of the gas existing on top of each other. And so it's 0 at short distances. But then it just goes straight to 1 because you would have complete randomization after that. So once you get past the regime of atoms overlapping each other, the structure after that is totally disordered. And so the G of R just goes directly to 1. And this would be for a monatomic gas. If you have a diatomic gas, like oxygen gas or nitrogen gas, then the first nearest neighbor position is very well defined by the bond, like the oxygen-oxygen bond or the nitrogen-nitrogen bond, but then you'd have complete disorder after that. Now, if we're in the liquid state or the glassy state, here we are somewhere in between these two extremes with both the liquid state and the glassy state. The short range order here for the first nearest neighbor is well defined. That gives us the first peak. The second nearest neighbor is somewhat well defined. Maybe you'll have some evidence of a bit of ordering at the third nearest peak, or maybe not. And then after that, it will converge to 0. You'll also see that the pair distribution functions of the liquid state and the glassy state are very similar because the structure of the glass is essentially the frozen-in structure from the liquid. How do we measure the structure of materials? The most commonly used method is X-ray diffraction. With X-ray diffraction, you are radiating the sample with X-rays, and then you can measure the diffraction pattern, and the diffraction pattern is going to show you if there's order in your structure, and the positions of the peaks, the intensities of the peaks would correspond to that structure of the material. And so if you use X-ray diffraction on a perfect single crystal, what you would see is a pattern as shown on the bottom here. Here you've got these perfectly sharp peaks. The peaks are perfectly sharp because it is a perfect crystal where all the unit cells are repeated perfectly in space, and the positions and the intensities would reflect the structure of that particular crystal. So if you're measuring the X-ray diffraction pattern of a perfect crystal, it would give you a set of peaks as shown on the bottom, and then you can use an X-ray crystallography database to look up what is the structure of that crystal and match your X-ray diffraction pattern to the known structure of that crystal. And there's very good software for doing that now, so it's very easy to identify what the crystal is in a material using X-ray diffraction together with those known databases. On the other hand, at the other extreme, if you have a glassy sample, what you will get from an X-ray diffraction pattern looks like what's shown on the top here, where you have kind of this hump, and this hump is generally known as an amorphous hump, although more properly, it should probably be known as a non-crystalline hump because the same type of hump exists in both glassy materials and amorphous solids. It exists in both because both types of materials are non-crystalline. Both glasses and amorphous solids have non-crystalline structures, and that lack of crystallinity means that instead of having all these sharp peaks, you just kind of have this hump with a bunch of noise around the hump. So if you have a sample and you don't know if it is a non-crystalline material or a crystalline material, you can tell very easily by doing an X-ray diffraction experiment. If all you see is this so-called amorphous hump, then you know that it is a non-crystalline material. It could be either a glass or an amorphous solid. Or if you see all of these well-defined peaks, then you know that it is a crystal. Now, it's also possible that you'll see something in between. So for example, some glasses may have crystals embedded in them. We're going to learn more about this further on in the course. But things like a laser pattern glass, where lasers are used specifically to grow crystals at given locations in the glass, or a glass ceramic, where crystals are thermally grown. there will be a combination of crystal phases and glassy phase. And as a result, the X-ray diffraction pattern will exhibit features from both. It will show peaks, and those peaks correspond to the crystals that have been grown, but it will also have some degree of this amorphous hump, which represents the glassy matrix phase. And the kind of balance between the sharp peaks versus the amorphous hump is governed by how much of the volume fraction of your material is crystal versus still in the glassy phase. So if the material is mostly glassy with just a small amount of crystals, you will see something that looks a lot like this amorphous hump, just with a few peaks on it, a few small peaks. As the crystals grow over time, the amorphous hump becomes less and less, and the crystalline peaks become more and more well-defined and become higher in intensity. What this means is that X-ray diffraction is actually a great tool to determine the crystallinity or lack of crystallinity of a sample. So if you are trying to make a glass, one of the first experiments that you should do on your sample is an X-ray diffraction experiment, because that will tell you, did you in fact make a glass, or did you make a crystal, or did you get something in between? So X-ray diffraction is one of the key tools, because it can very quickly and easily tell us if we're making a sample, is it a non-crystalline material or is it a crystalline material? And if it is a crystal, what are the types of crystals that are observed? So to summarize this particular lecture, the definition of glass that we covered last time is independent of chemistry. So this definition can be applied to any type of chemistry. So in principle, any liquid can be quenched into the glassy state, which means that there are an infinite number of possible glass chemistries available. And that is because of this non-crystalline structure of glass. And but that doesn't mean that the structure is completely disordered. What we know is that the non-crystalline structure of glass actually exhibits some short-range order, meaning that the first nearest neighbor is fairly well defined. But if you go to longer range distances, that we have disorder at those longer distances. And we can quantify the structure of glass. It's captured by its pair distribution function, or equivalently, the radial distribution function. I'd like to finish this lecture with one of our glass greats, and the glass great for today is Alfred R. Cooper. Alfred R. Cooper is actually my academic grandfather, meaning that he is my advisor's advisor. So my advisor is Professor Arun Varshney, who's the first author here on the textbook, and his advisor was Professor Cooper. Professor Cooper was born in 1924 and lived through 1996. So I never actually got a chance to meet him, but I hear many great things about him from Dr. Varshney and from some of his other students. He was born in New York City, and he went to school at Alfred University in upstate New York. He enrolled in Alfred's glass technology program in 1941. His studies, came at a time when the world was at war, and they got interrupted by World War II. So during his undergraduate studies, Al Cooper actually joined the U.S. Navy as an officer in 1943. After the war was over, he returned to Alfred and completed his Bachelor of Science degree, which he finished in 1948. From there, he went to work in the glass industry. First, he worked at RCA and then at Emhart Corporation. And then he went back to school to MIT to get his Doctor of Science degree, which he completed in 1960. He then stayed at MIT. He joined the faculty there for a few years, but then in 1965, he moved to Cleveland to Case Institute of Technology, where he founded the ceramics program there. And he created one of the best academic ceramics programs in the country at Case Institute of Technology. Case Institute of Technology later merged with Western Reserve University, becoming Case Western Reserve. So that is what the university is known by today in Cleveland. And Cooper is known for being a really great mathematician and physicist. And he brought a lot of physical and mathematical rigor to the study of glass science and technology. Prior to his work, a lot of the understanding was just kind of um, empirical observations. And what Cooper was able to do is to take those empirical observations and bring some mathematical and physical rigor to that understanding. He was also very well known as an educator of glass science and technology, and his legacy lives on both through his students as well as his academic grandchildren and now great-grandchildren. So thank you for watching, and next time we're going to get into chapter 3. We're actually going to spend the next 3 lectures on chapter 3, where we get into more specific theories of glass formation. We're going to discuss what makes a good glass structure versus what makes a poor glass structure. And next time we will get into structural theories of glass formation. So thank you very much, and I will see you then.